with this concept of distribution of particles in various manners, let us talk of this distribution of particles in different manners with different weight factors as distribution of particles in different states. Okay, it is like as we have distributed the coins while tossing. For every toss, well, an event is occurring. Similarly, when the particles are actually moving, or even if they are at rest, they are actually present in a particular state. So we will study actually how the particles are distributed therefore in various states, as we have talked about the coins, distribution of coins under different states of tossing. Okay, now when we talk of states, we would like to introduce something called macro state and something called micro state. So basically we would be talking about macro state and micro state. Okay, now these two we will be discussing. We will define my macro state or micro state subsequently, but before that let us discuss this again with an example. Alright, suppose we have, say, 4 distinguishable particles. Suppose, say, we have 4 distinguishable particles. Okay, so, and we wish to distribute them into 2 exactly similar compartments in an open box. Because why exactly similar? So, to be distributed in exactly similar, so this exactly similar compartments. Okay, so we would like to distribute this in exactly similar compartments in an open box. Okay, why this exactly similar? Because we would like to retain the condition of equal a priori probability. So this is very important. Okay, so since the particles are distinguishable, let us signify the particles as, because the particles are distinguishable, let us signify them as A, B, C and D. Okay, let the particles be signified in this manner. So any particle thrown into the box must fall into one of the compartments. Since both the compartments are equally alike, the particles have the same a priori probability of going into either of them. So in other words, the probability of particle falling in any component, what is the probability? Well, this will be, so what will be the probability? Because it is distinguishable, the probability that the particle falls into any one of the compartment will be half, isn't it? Because that's what we know from the tossing of coins if you have a head and a tail. Now the two compartments may differ only because of some property. What are the properties? Maybe energy, momentum or velocity of the particle. So suppose we take the property as energy of the particle. Let each particle occupying compartment 1 have energy E1 and the particles occupying compartment 2 have energy E2. Okay, so suppose, say, we have 2 compartments like this. Okay, obviously they will be of equal size to invoke the condition of equal a priori probability. So the first compartment will have energy, suppose say E1, and the second compartment, suppose say particles belonging to this compartment will have energy E2. Okay, so now if we distribute, suppose say, the particles into the compartments. Suppose say this is your compartments. So here you have two compartments, then you have distribution 1, distribution 2, distribution 3, distribution 3, distribution 4, and you have, suppose say, distribution 5. Distribution 5. Okay, what are the possible ways? So compartments and the distributions 1, 2, 3, 4, 5. What are the possible ways? So compartment 1, you 4 particles, na? So you may have no particles here, whereas in compartment 2 you may have 4 particles. Here the second distribution is you may have 1 over here, 3 over here, you may have 2 over here because you have 4 particles, na? You may have 3 over here, 1 over here, and you may have 4 over here and 0 over here. So these are your 4 distributions. So there are 5 different distributions. You are having 5 different distributions, isn't it? You are having 5 different distributions. What are they? 0, 4, 1, 3, 2, 2, 3, 1, 4, 0. You have 5 different distributions. So each compartment-wise distribution of a system of particle, each of these compartment-wise distribution of a system of particle, each of the distributions, these distributions, well, they form a macro state. We call this a macro state. Okay, what then is a micro state? What then is a micro state? Here the particles are distinguishable. Each compartment wise distribution can have similar arrangements. Okay, so can have arrangements in the manner shown. Now if you want to try to find out the total number of microstates, you see you have to look into the table in a different manner. What is it? See, you will have for microstates, for search for microstate, search for microstate. Okay, search for microstate. Let me write it here, otherwise maybe when you see it there it won't be visible. You will consider the table in this manner. What is it? Macrostate. Suppose say you consider macrostate, then you consider your compartment number 1, compartment number 1, compartment number 2, compartment number 2, and then the number of microstates. Suppose you are trying to find out. Now you will see how it differs, number of microstates. Okay, so you will see how things differ. For example, if you take the first macrostate, take this macrostate 0, 4, take the macrostate 0, 4. Okay, compartment number 1 0, and in compartment number 2 you have A, B, C, D, all 4 particles. So number of microstate is 1. Consider the macrostate 1, 3. Consider 1, 3. Okay, for 1, 3, you see your, it can be A, B, C, D, isn't it? It can be B, A, C, D. It can be C, A, B, D. It can be D, well, A, B, C. How many microstates you are getting? See, now you are not getting one. Now for one macrostate, you are getting 4 microstates. Okay, similarly, if you do the same for 2,2, suppose you do this for this one, 2,2. Alright, if you do it for 2,2, what will you get? See, AB, CD, AC, BD. Like that it will go on. Okay, and you can show that this number is equal to 6. For one macrostate 2,2, you are getting 6 microstates. And now if you try 3,1, now if you try 3,1, just like 1,3, 3,1 means it will be like B, C, D, A, like this. So it will go on, and this will again be 4. And then if you try 4,0, you have seen already 0, 4. Now if you try 4 zeros, that means A, B, C, D, 0, this is 1. So total number of microstates, if you just add up, how much are you getting? If you just add them up, it is 16. Isn't it? So this is actually equal to this total number of microstates, 16, which we are saying 16. This is actually equal to 2 to the power of n. This is actually equal to 2 to the power of n. Okay, where n is the number of particles. Alright, so you see, what is the explanation? So if we consider a physical system composed of n identical non-interacting particles in a space of volume V, and let the particles have ni number of particles have energy, say EI, then in this case what can we say? You see, we can say that this is the following that we can say over here. What is it that we can say? You see, for n number of particles having energy composed, if you have suppose say n identical particles which are non-interacting in a space of volume V, and let ni number of particles have energy EI, then we can say that this energy E is actually equal to the summation over I ni EI, where n, capital N, is equal to summation over I ni. Isn't it? So you see, the possible values of single particle energy EI, we know from quantum mechanics, these are discrete and hence have E as the discrete value. And well, the volume V is obviously very large. So the specification of the actual values of the parameter N, V and E, the specification of the actual values of the parameter N, V and E defines a macrostate. Okay, so if you would like to actually have the more appropriate definition, because you get this question, define a macrostate with a proper example, then in an isolated system consisting of a fixed number n of non-interacting identical particles having fixed internal energy E and occupying a fixed volume V is said to be the macroscopic state or macro state of the system. That is just the answer. Alright, how do you define a microstate? So, well, each of the different ways in which the total energy E of the system can be distributed among the n particles constituting it specifies a microstate. So, you have seen how for every macrostate, the different ways in which the total energy E can be obtained. It's different, isn't it? So the same energy E can be obtained in 4 different ways. If you just go back to this example, that we did just now. This example, the same macro state of specific energy can be obtained in 4 different ways. Okay, here it can be obtained in 6 different ways. Here again in 4 different ways. That means you are getting the same energy value. What do you call it? You have learnt it in quantum mechanics. So systems with same energy value, what do you call it? Well, the number of quantum states for a given energy level is called the degeneracy of the level. I have given you a problem also in your test in quantum physics. So this is the degeneracy that you see of a system having the same energy value. 4 in number, 3 in number. So each of the, how do you define therefore a microstate? You see, so here, how do you define therefore a microstate? A microstate, therefore, just as you have defined the macrostate with N, V and E, each of the different ways in which the total energy E of the system can be distributed. Different ways in which the total energy E of the system can be distributed among n particles constituting it defines the microstate of the system. Why am I writing it down? Because you get it in your exam. Microstate of the system defines the microstate of the system. So thus to a given macrostate, therefore for a given macrostate you get a definite number of microstates. Okay, there may be one or many microstates. So let us stop our class today over here with the definition of energy levels, with the definition of macrostate, microstate and the corresponding energy levels that we get. Okay, the concept of energy levels and the concept of degeneracy which emerges from these definitions of macrostate and microstate. Usually in your question you get define a macrostate or microstate with a suitable example. So I would like all of you to write it down in your assignment copy and you submit it when the college will open. So please write down this question. Define a macrostate and a microstate with a suitable example. Is it okay?